Hello, so this is a warm-up video for the IGCSE second paper. What I've done is I've had a look at the first paper and then compiled some past paper questions based on topics that didn't come up in the first paper. So these are potential questions, if you like, for the second paper. They're all based on some quite old IGCSE questions going back sort of pre-2008, but the content is still relevant, and hopefully this will be a useful warm-up for that final exam. So here's the first question. So you'll notice that I've sort of cobbled this together from sections of other questions, and in this question the question is about, or this part, certainly the first part here, is about the reactions of ammonia, and the first bit which I've included here is a test for ammonium ions. Now ammonium ions are NH4+, and you can test for those by reacting the solution that contains ammonium with sodium hydroxide. Okay, now I'm just writing out the equation for what happens, and what does happen is the ammonia combines with the sodium hydroxide, or the hydroxide ions in the sodium hydroxide, to produce ammonia gas. And so you then warm the mixture, and that releases the ammonia, and that can be tested with damp red litmus, which turns blue. So your 3 points here are react with NaOH, warm, and then gas turns red litmus blue. And really it should be turns damp red litmus blue. My writing is atrocious, but I'm trying to write quickly, so please forgive me for that. Now, the next question is talking about making a salt using aqueous ammonia and hydrochloric acid. Now, both ammonia and hydrochloric acid are soluble, and the product, ammonium chloride, is also water soluble. So we're producing a soluble salt from a soluble base, and so we're going to use a titration method. Okay, now earlier in this question there was a little bit of work on titrations, so here I'm not going to go through the full titration method, but talk about measuring out a specific volume of ammonia into a conical flask, putting hydrochloric acid in the burette, adding the hydrochloric acid dropwise until a neutral point has been reached. Of course, you're going to have to know that neutral point by using an indicator. So in there, talk about the colour that the indicator would turn, and then repeating the process without the indicator, and only going as far as the neutral point. And then when you've got that neutral solution, you need to form crystals. So you obviously can't filter it because the crystals have dissolved in the water. So gently warm the solution until probably half the water has been evaporated, and then leave the rest of the water to evaporate naturally. You're not going to want to heat it too strongly, otherwise you might thermally decompose the ammonium chloride. Okay, so initially talk about your titration, and then talk about how you will get your crystals from the solution. The next question goes on to talk about insoluble salts, and in fact an insoluble salt was mentioned on the first paper, but I've left this in. Lead chloride is insoluble. Name two solutions that react together to make it. Well, you need to think of two things that are soluble to start with. One of those things needs to contain chloride ions, so you need to think of something which is water soluble that contains chloride. So I tend to think of sodium chloride, but you could choose hydrochloric acid, okay, or potassium chloride. Most chlorides are water soluble. And then you need to come up with something that contains lead ions, which is also water soluble, and probably in your lessons you'd have seen lead nitrate used to make your insoluble lead compounds. So the lead nitrate supplies the lead, sodium chloride will supply the chloride. Now this question is predominantly about energetics, but there are some organic questions thrown in here just for good measure. So we're talking about the conversion of ethane, an alkane, into an alkene, ethene, and releasing hydrogen gas. And the question kicks us off with actually state a use of the products formed in this reaction. Well, hydrogen has got a number of uses. It could be used as a fuel, or it could be used in the Haber process to make ammonia. And my writing's getting even worse. Ethene, well, hopefully you've seen that it is willing to undergo an addition polymerization reaction. So ethane is used to make polymers. And now the energetics kicks in. Now they've told you here that it's an endothermic reaction, and hopefully you should know that delta H for an endothermic reaction is positive. So in other words, the products will have a higher energy than the reactants. So if we're showing this on an energy profile diagram, we've got our reactants down here, and the amount of energy in the system is going to increase. So the energy level of our our products, is going to be way up here. And we'll label that C2H4 plus H2, and we usually put on a little bit of a line to go between, and I'll leave it as that. In this case they haven't asked you about the activation energy, and that would be that distance there. And what I will also do here is I will label delta H, so that goes from the reactants to the products, and delta H is positive. Now we don't actually know how endothermic the reaction is, but surprise surprise, that's what the question goes on to ask us in a moment. And in order to calculate an enthalpy for this reaction, we need to draw out what we call displayed formula. Now a displayed formula of an organic substance shows all the bonds with little sticks, as you can see with hydrogen. Now ethene is an alkene, so it has a double bond between the carbons, and each carbon therefore needs two more bonds, and those are hydrogens on it, like so. And ethane is an alkane, so only single bonds. Each carbon has 4 bonds, like that. Now the next question asks us to calculate the energy change of the reaction using the bond dissociation energies up here. And now I've just paused the video, and in that pause I was playing around with the controls. I've managed to move the screen around a little bit, but I've also managed to insert a massive arrow in here, which I don't really want there, but I don't know how to remove it on this program, so I'm afraid we're just going to have to do the rest of the question with the massive arrow in the way. So we are looking at the enthalpy change for this reaction, and we're going to have to calculate the energy required to break all the bonds initially. So bonds broken, and let's have a look at the bonds we've got. Well, we've got in our reactant 1, 2, 3, 4, 5, 6 CH bonds, and we've also got 1 CC bond. Okay, now we can look it up in the table. So we've got 6 times 4.12, which is the CH, and then we've also got the CC, which is 348, and if we do that quickly on the calculator, that comes out as 2820. Bonds made, well, when we make bonds, we release energy. Okay, now we're expecting overall the reaction to be endothermic from what was said on the previous slide. So bonds made, well, we've made 1, 2, 3, 4 CH bonds. We've made a CC double bond, okay, and we've made an HH. So CC double bond is 612, HH 436, and 4 times CH, so that's 4 times 412, okay, and that comes out as 2696. So the delta H is always calculated breakup minus makeup, so it's 2820 minus 2696, and that gives, I'm just doing it on the calculator, 124 kilojoules per mole. Okay, and I always put in the sign just to emphasize that it's a positive number and therefore it's an endothermic reaction. I'm just going to pause it there. Hopefully the next time I pause it, a massive arrow won't appear, and that's going to be the end of the first part of this video.